Hello, everyone. Today I'm going to talk about 1588 peer-to-peer transparent clock. 1588 standard second version was released in 2008. In this version, the following entities for the call: ordinary clock, peer-to-peer transparent clock, end-to-end transparent clock, boundary clock, and management node. The 1588 version 2.1 released in 2019. In this new version, defined few entities called PTP instance, PTP node, boundary clock, ordinary clock, transparent clock, local clock, local PTP clock, and PTP management node. This is some new entities defined in the new version. In the 2019 version, which means version 2.1, transparent clock, how transparent clock works, described in the chapter 11. This is the master clock, the transparent clock, and the slave clock. How slave clock to adjust local clock to align with master clock. There are two steps. First step called calculate offset from master on the slave clock. The formula: offset from master is the time on slave clock minus time on the master clock. After calculate the offset from master, adjust local time on the slave clock. After these two steps, the slave clock will be synchronized to the master clock. For example, the master clock, the current time is 1 o'clock. After while the message received on the slave clock is 1 o'clock 1 second. So the offset from master is 1 second, calculated on the slave clock. After calculate offset from master, adjust local clock by 1 second. So after that action, so the slave clock is 1 o'clock 02 seconds, and the master side is 1 o'clock 02 seconds, which means the slave clock synchronized the master clock. Same thing in the 2019 version. Two types of transparent clock defined. First one called end-to-end transparent clock. Second one called peer-to-peer transparent clock. The end-to-end how the end-to-end transparent clock works, I create separate video. You can check the YouTube. And for this video, we are going to focus on the peer-to-peer transparent clock. The peer-to-peer transparent clock, here three from master TC to transparent clock slave. There are three different time delays introduced. First can mean link delay between master and slave, and package going through the transparent clock from ingress port to the egress port. That part delay called residence time. Another side part delay is between transparent clock to the slave. It's called mean link delay. We can call mean link delay number 2. Here it's called mean link delay number 1. So this total offset for a master calculate on slave side equals mean linked delay number 1 plus resident time plus mean linked delay number 2. So the time on slave equals time on of the master minus offset from master. So for the peer-to-peer transparent clock, we mentioned 3 different delays. One is called resident time. Resident time means the PTP message coming from grandmaster arrive on the ingress port. After that, on the ingress port, make ingress timestamp. After going through whole entire transparent clock, the message going out from transparent clock. When the message going out from transparent clock on the egress port, make another timestamp called egress timestamp. So based on these 2 timestamps, the PTP will calculate resident time on the transparent clock. So the resident time on the transparent clock is egress timestamp minus ingress timestamp, which means the 1 o'clock 15 seconds minus 1 o'clock 10 seconds. The result is 5 seconds. Yeah, this is the delay introduced on the transparent clock. For the peer-to-peer transparent clock, there are 2 different types. First one called one-step transparent clock. Second type called two-step transparent clock. So discuss one-step transparent clock. So when the master side sends out sync message received on the ingress port on the transparent clock, and the message coming out from egress port, they generate another timestamp called egress timestamp. So after 2 timestamps generated, the TC calculate resident time based on 2 timestamps. Resident time equals egress timestamp minus ingress timestamp. After calculation finished, forward sync message out. However, the sync message, the correction field of sync message will be modified based on calculation on the resident time and mean link delay between master and slave. So the correction field of sync message, there is a new sync message equals mean link delay between master and TC plus resident time calculated by the TC. So if the master sends out follow-up message, which means master side is two-step master. So after receive the follow-up message on the transparent clock doesn't do any change for the follow-up message, just forward it to the slave side. This is how the one-step peer-to-peer transparent clock works. So another type of peer-to-peer transparent clock is a two-step transparent clock. For the two-step transparent clock, there are 2 different scenarios. First one is TransparentClock received sync message. The two-step flag is false. Second scenario is the sync message two-step flag is true. These two different scenarios for the two-step TransparentClock. For the scenario number one, the sync message the flag, two-step flag is false, which means no follow-up message will be received on this TransparentClock. So after the TransparentClock received a sync message on the ingress port and generate first timestamp called ingress timestamp. And when the message is coming out from egress port, generate the second timestamp called egress timestamp. So after the two timestamp generated, the TransparentClock doing calculation for the resident time. For the two-step TransparentClock for the sync message doesn't do any modification. However, will generate one new message they call follow-up message. The calculated resident time and the mean link delay between master and TransparentClock will be added together, put in the correction field of follow-up message. So correction field of follow-up message equals mean link delay 1 right here plus resident time introduced by the TransparentClock. For the sync message, no modification. The origin timestamp of received sync message will be copied to the follow-up message. This is the first scenario for the two-step TransparentClock. The second scenario is the sync message two-step flag is true, which means follow-up message will be received on the ingress port of TransparentClock. So after received sync message on the ingress port will generate first timestamp called ingress timestamp, and then send it out the sync message. When send it out sync message, generate the second timestamp called egress timestamp. And then doing calculation for the resident time. Resident time equals egress timestamp minus the ingress timestamp. Because this sync message two-step flag is true, which means the follow-up message will be received on the ingress port. After received the follow-up message, the TransparentClock will modify correction field of the follow-up message. Put both mean link delay number 1 and resident time together, put in the correction field of the follow-up message and then send it out. So correction field of follow-up message equals mean link delay number 1, which means between master TC plus resident time and then plus correction field of received follow-up message, which means this follow-up message, the correction field includes three different parts. First one is the link delay between master and TC. Second one is the reset time on the TC. The third one is received original correction field from the follow-up message. For the sync message, no modification. This is how does the two-step peer-to-peer transparent clock work. So we mentioned we need to calculate the link delay between master and the transparent clock. Here the mechanism is called peer delay calculation. The transparent clock at timestamp T1 send out peer delay request message. On timestamp T2, master side received the peer delay request message. On timestamp T3, master side send out peer delay response. On the timestamp T4, transparent clock received peer delay response message. So based on T1, T2, T3, T4, the transparent clock calculate mean link delay. The mean link delay equals time response to request plus time request to response divided by 2. So for the timestamp is T2 minus T1 plus T4 minus T3 divided by 2. Based on this formula, the transparent clock can calculate the mean link delay between master and transparent clock. So we mentioned the second link delay between transparent clock and slave. How calculate this link delay? So on timestamp T1, slave side sends out the peer delay request. On timestamp T2, transparent received the peer delay request. On the T3, transparent clock sends out peer delay response. On the T4, slave side received the peer delay response. Similar formula for the slave side. Slave will calculate the mean link delay between slave and transparent clock. The T2 minus T1, T4 minus T3 divided by 2. That's the same similar calculation. So this is the mean link delay number 2 will be is calculated by the 4 different timestamps. So after resident time mean link delay number 1, mean link delay number 2, the slave side can calculate offset from master. So this is the formula. Sync event ingress timestamp minus precision origin timestamp minus mean link delay number 2 minus correction field of sync message minus correction field of follow-up message. Based on this calculation, the slave side got her offset from master. So this is the whole procedure. Sync message sent out from master going through transparent clock with slave, and followed message sent out from master which transparent clock received on slave side. So the peer delay calculation between master and TC and the peer delay calculation based on timestamp finished by the slave side. So everything done. After that, the offset from master calculated. So after offset from master calculated, slave side adjust local clock time. We talk about how does peer-to-peer transparent clock works, include both one-step and two-step TC. So next one, I'm going to give you some example for both one-step P2P TC and two-step P2P TC. So here's the topology. Include three different devices. First one, the Broadcom RFG2488, one-step master. Broadcom RST2228, one-step transparent clock. Broadcom RMC8388A3. Because we are testing the peer-to-peer transparent clock, we choose utility profile, configured all three devices. The fourth device and the third device configured as ordinary clock, and the middle one is peer-to-peer transparent clock. So after configuration finished, we can check the clock status. The first one running as master, the middle one running as peer-to-peer transparent clock, and the last one running at sleep. The current offset is -30 nanoseconds. So we can use the PC to connect to the three devices doing very short capture. See what the message looks like. So this is the sync message because it's a one-step master. So we capture a message on the transparent ingress port, this one, and transparent clock the egress port. We use the message here. So we capture same message, which use the same 2128 sequence ID. So because the correction field received is 3133646768. The egress port is 31667116. So we can see the correction field has changed by the transparent clock. So the sync message sent out from master received on the ingress port of transparent clock, and transparent clock modify the correction field and then send it out to the sleep side. So this is the resident time for the sync message. It's timestamp. Sorry, not time. It's the correction field. This one minus this one equals. So the resident roughly 2.3 microsecond. So sync message. This is calculated by based on sync message. The second scenario is the grandmaster sends a message include sync message and follow-up message, which means ground must run as two-step. So you can see two-step master configure here, and peer-to-peer transparent clock on the middle device, slave configured on the third device. So after configuration finished, we can see slave set the offset from master is around -30 nanoseconds, which means slave set synchronized with master set. So we do the same thing, capture message on the ingress port of the transparent clock and the egress port on the transparent clock. So this is the sync message received on the TC ingress port sent out on the TC egress port. So we have the correction field on the received sync message is 0. After sending out, the sync message correction field is 2206, so around 2.2 microsecond. So this sync message received and sync message send it out, calculate return time in the 2.2 microsecond by the transparent clock. So we mentioned the because the master side is the two-step master, send it out follow-up message as well. The transparent clock received the follow-up message on the ingress port. So this we can check the follow-up message correction field is 0. So after the egress port send it out the follow-up message, we capture again to see the correction field is 0, which means the follow-up message nothing changed for the correction field. So this is a sync message, nothing changed. Next, next example is two-step peer-to-peer transparent clock. So we still use 3 devices. First one is the Ruggedcom RSG24888 one-step master, and the middle one is the Ruggedcom RSG909R two-step peer-to-peer transparent clock. The third device is the Ruggedcom RMC83888 slave clock. So there is the configuration. So ordinary clock configured on master and the slave, and two-step peer-to-peer transparent clock configured in the middle between the RSG909R. So after configuration finished, we can check clock status. This one running as master, that's running as transparent clock. The third device running as slave. The offset is -30 nanosecond, which means synchronized with the master clock. So next one, we are going to capture PTP message on the ingress port of transparent clock and also egress port on the transparent clock. Because this master is the one-step master, we only can see sync message on the ingress port. Is no follow-up message. So in ingress, the sync message correction field sync message is that value. On the egress port, we capture sync match as well. The correction field is 0. So which means this clock will doing one step to the two-step conversion. So sync message received, I just send it out. However, after sync message send it out, the two-step transparent clock will generate the new message with a follow-up message. So we can see sync message and new follow-up message generated. We can capture the sync message on the ingress port and the follow-up message on the egress port. So the correction field generated based on the calculation on the two-step transparent clock. So it's a sync message, new follow-up received. New follow-up message generated. So the resident time is this value introduced by the two-step transparent clock. There is another example for the two-step transparent clock. If grandmaster running as a two-step. So we're still using these three devices, Broadcom RSG2488 two-step grandmaster, Broadcom RSG99R two-step transparent clock, and Broadcom RMC8388 sleep clock. So there's the configuration. We configure ordinary clock on both device number 1 and number 3, and we configure two-step peer-to-peer transparent clock on the second device. So we use utility profile for all the devices. So after configuration, we can see the first device running as master, second device running as transparent clock, third device running as sleep. So we continuously capture message on the ingress port of transparent clock and the egress port on the transparent clock. So here is the sync message for the two-step transparent clock. See, we received sync message and the check correction field is 0. Check sync message on the egress port, the correction field is 0 as well, which means no any modification happened for the sync message. So this sync message is received on the two-step transparent clock and just forwarded to the sleep side. So the correction field, nothing changed. So because it's a two-step grandmaster, the transparent clock will receive follow-up message. We can capture follow-up message on the ingress port and the egress port. So this the ingress port, the follow-up message. This follow-up message captured on the egress port. This we can compare the correction field modified by the transparent clock. So a follow-up message received on the ingress port and calculate resident time and modify correction field and then send it out by the two-step peer-to-peer transparent clock. Okay, Today we discussed how one-step peer-to-peer transparent clock works, how the two-step peer-to-peer transparent clock works, and we have an example for the one-step transparent clock and example for the two-step peer-to-peer transparent clock. Yeah, that's everything today. Thank you for watching. See you next time. Bye.